Good morning, everyone. And today we are going to talk about these polymer structures. And we have finished metals. We have talked about metals and metal alloys, ceramics, and then we are going to talk about polymer structures. And polymer structures, the polymer materials, also have been used in our daily life. Uh, and this is very important one. Even though and polymer materials they have different engineering applications from the metal and metal alloys along with the ceramics, but they have their special applications. So they are also very important. And here are today's objectives. And first, we want to learn the general structural and chemical characteristics of polymer molecules. And we want to learn some of the common polymeric materials, and we call it polymeric materials, and their chemical differences. So what is a polymer? And polymer actually it is we put the two words together. So this is poly. Poly means many, right? So in the English language, poly means many things. Mer, mer here is the repeat the unit. And this is repeat unit. And so look at this structure. Okay, this is a polyethylene. This is a polyvinyl chloride (PVC), and also this is polypropylene. So this is a PP. So this is a repeat unit, and you can see this is repeated units. Hydrogen, hydrogen, carbon, carbon, hydrogen, hydrogen. So this is one unit. If we have multiple and these kind of units, we call this a polymer. This is a polyethylene, PE. And so similarly, for repeat unit, if we have HCC, now H here, so another H is replaced by chlorine. This chlorine atom. So this one is forms. This is a new repeat unit, and so this is repeat unit is a polyvinyl chloride. So this is a PVC. And so here HHCCH, another H here. Okay, so we say this one is our original, original mer repeat unit. And so here is changed. This H is changed to CH3. So this is one single repeat unit. If we have multiple this kind of unit, and we call this is a polymer, polypropylene, so PP. Any questions regarding this slide? So this is very interesting if you memorize the polymer this way and to just and decompose this polymer into two components. One is a poly, one is a mer. It is much easier. It makes perfect sense for understanding. So this is what a polymer is. Any questions so far? Keep in mind, poly means multiple, many. Mer means unit, repeat unit. And ancient polymers. And as I said, polymers have been very materials for human being. And also, actually, it is for a very long time ago, the humans ancestors started using these polymers. For example, originally natural polymers were used: wood, right? Cotton, leather, rubber, wool, silk. So all these materials are natural. We call them natural polymers, and now they are being used also now. But and since many years ago, humans ancestors started using them: wood, cotton, leather, rubber, wool, silk. And this silk is very in some areas in China, people use the silk very um, widely. So all these known uses: rubber, the balls used by Incas, rubber boards. Noah used pitch, a natural polymer for the ark. Use a pitch for the Noah's ark. You know Noah's ark, right? So this Noah use the pitch for the ark. Any questions regarding this slide about ancient polymers? Human ancestors have been using since many years ago. 认为 polymer composition. So we know the polymer. Okay, most polymer are hydrocarbons. Most polymer are hydrocarbons. You can see it is H and C, and that is made up of hydrogen and this carbon. And one is saturated hydrocarbons. Saturated hydrocarbons. Each carbon are singly bonded to 4 other atoms. Unsaturated. Each carbon singly bonded to 4 other atoms. So for example, this ethene C2H4H6. So this is C is a bond, and this C has is bonded to one carbon, another carbon here, along with other 3 hydrogen atoms. And same thing for this carbon. So this is also this guy is bonded on this carbon atom along with these 3 hydrogen atoms. So you can see this is the chemical formula is C2H6. This is called saturated. Right? Saturated means that, and C, because C is outermost, the electrons in the outermost layer for the carbon is 4, and this guy wants to reach number 8, the number 8 of 8 electrons in order to be chemically stable. And how to do that? And they share, they have single bond with the C here and hydrogen here, and so they can just form a chemically unstable. This is the structure. And so here are compositions and molecule structures for some of the paraffin compounds. Paraffin compounds, this is a CnH2n plus 2. So name, composition, structure, chemical structure, along with their boiling the points. You keep in mind this is boiling the points. This is a very soft material. Methane is commonly used one CH4, not just for polymer but also for the case hardening. And when I taught you the case hardening, we can use the methane, the gas, in the sealed the chamber, and in order to case harden, this is the samples. And ethene is C2H6, propane C3 and H8, butane C4H10, pentane C5H12, hexene C6H4. So these are paraffin compounds. The chemical formula is given as follows, as this one. This is the structure. Okay, so you can see structure of boiling points, and they are given here also. You can see this is negative 164, and this is very low. And so for the hexene, and the boiling point is 69, and so this is a degree C. Any questions regarding this slide? No question? An unsaturated anhydrocarbon. Unsaturated carbon means that double or triple bonds somewhere unstable and can form new bonds. So this you can see, this is a double bonds between these two carbon atoms in ethylene or ethene. And so this, as I said, the double or triple is not stable and somewhat unstable. That means chemically they are active. That means it is the C has a tendency to have chemical reaction with the neighboring items in order to achieve more stable state. So triple bond found in actylene or this ethene. And for here, you can triple bond. Triple bond means that this C and is bonded only to one hydrogen atom, and this C is also bonded only to one hydrogen atom. And between these C's, we have three bonds, triple bonds there, triple bond. Any questions so far? No question. And then isomeric, isomerism, isomerism. So iser, in English language, iser means that something is the same. Okay, so here, what is the same? Mer is the same. And isomerism means two compounds with the same chemical formula can have quite different structures. Do you have sense? For example, C8H18. So isomerism. And so here normal octane means 8. So this is CC, and so this is H, this is 1H, this is 1H. And so here, this equals, and this one, okay, H3C, C2, CH2, until this here, this CH3. And we can see this one can be written as, using this is the formula. There is not another one is a 2 or 4 dimethylhexene. And so here you can see clearly that so this one is different from this. Right? So CHCC, CH3, CH2, CH2, CH3, and CH3. And why it's called 2,4? Because this happens at the second and fourth. This is the carbon atoms on this branch. Any questions so far? So we have a lot of very, very interesting the words here, and so you need to make sure you know how to pronounce it, how to spell it. Maybe in next class we can have some spelling tests. How does that sound? I hope you will hate this idea, right? Okay. So let's move on to next slide. So polymerization and polymer chemistry. And polymerization, we mean that, and we make the mer to become together. And we can see here, okay, so free radical polymerization. So here is the free radical, and here is a monomer. Okay, this is a monomer, and we call it monomer repeat unit. And so these two guys come together, and we call this initiation, right? So this initiation, and then the propagate. So this guy and comes to another when this guy meets another monomer, okay, this another monomer, and then this C and this C, and they just form a new bond here. So this is a propagate. We call dimer, or called dimer. So this is the means 2. Initiation example and benzoyl peroxide. This is a benzoyl peroxide. And here the COOC, another one. We have 2 here, and we have this 2R, 2 radical. So initiator. So we can see this is a circle, okay? This benzoyl, this is a circle. Chemistry and the structure of polyethylene. So this is repeat unit. This is the chemistry and structure of polyethylene. You can see this is a 3D. You can see it's a 3D, and this is a carbon, and smaller is a hydrogen. Note, polyethylene is a strong chain hydrocarbon. Strong chain, very strong. Paraffin wax for kettles is a short polyethylene. And bulk or commodity. on polymers. So a list of repeat units for 10 of the more common polymeric materials. So this is polyethylene, PE, polyvinyl chloride, PVC, this one. At the very beginning, I talked this one. So the polytetrafluoro, this is called polytetrafluoroethylene, PTEE, and polypropylene, PP. So they have different repeated unit. And also here is a polystyrene PS, and here is a bezel. Here's a bezel here, and polymethyl methacrylate and PMMA, and phenyl formaldehyde. This is have a bezel there also, and this is hexylene adipamide. Okay, so this is a polycarbonate on PC, and there are many very very useful polymers. And here, okay, this is our old friend and VMSE. And as I said, if you have uh, bought your own textbook, and then along with the textbook, and you should have these resources, and so you can use this as a software and to visualize um, the repeat unit structures for polymers. And then we talk about molecular weight. Molecular weight, okay, so molecular weight M, mass of a mole of chain, and this is a low uh, molecular weight because and this is a chain is short, and so this is a high molecular weight. Why? Because and so this guy has a very very long chain, and not all chain in a polymer are of the same length. And that is there is a distribution of molecular weights and distribution molecular weights. So even in the same material, different branches, different chains, and they have different lengths, and you need to be very, very careful. So here is a slide. This slide shows the distribution of molecule size. So this molecule size, right? So here this molecular weight. So this number fraction is given here. And for this is a molecular weight, and so this weight fraction. So molecular weight distribution, and also Mn means that total weight of polymer divided by total number of molecules. This is a molecule, okay? The molecule, total number of molecules. So this Mn equals sigma xi mi, and so this I can see mi is the mean middle molecule weight of size range I, and xi number fraction of chains in size range I, and W is weight fraction of chains in size range I. So this is a 2. So this is a Wn is W MW, Mn and Mw. So this is a number averaged Mn. So Mw is a weight average, weight based on the weight, and the number we average is based on the number fraction of chains. Molecular weight calculation. Example: average mass of a class, a student, and this is a student, and so this is weight. And what is the average weight of the students in the class? So this is a student index. Student index. This is a weight mass, and based on the number fraction of students in each mass range, number of students, and based on the weight fraction of students in each mass range. So this will give you an example on how can we calculate Well, how can we calculate this is the molecular weight? Molecular weight calculation, right? Solution, the first step is to sort the students into weight range. For example, using 40-pound ranges given the following table. Right? You can see, for example, weight range from 81 to 120, 120 to 160, until we have 360 to 400, and we see how many students weight are falling in this range, and we can write down this mean weight Wi, and calculate mean weight, and then calculate the number and weight fraction of students in each weight range as follows, using these two equations. For example, for the 81 to 120 pound range, so for this is the uh, the number fraction of students, and it is only two students, and divided by total equals 0.2. And the weight fraction, weight fraction, okay. So these two guys weight is 2 multiplied by 110, and the total weight is 1881. So this gives us 0.117. And then we have, this is the weight range, mean weight, number fraction, weight fraction, and we write this one as in the table. And then we calculate this Mn based on this equation, and Mw based on this equation. And we can see these two values, and they are quite different for this example. Any questions so far? And so you need to know how to do the simple calculations using these two equations. And then we talk about the degree of polymerization, or dP. And dP means the average number of repeat units per chain. Right? So per chain average. For this one, dP equals 6. dP equals Mn number average molecular weight divided by M bar, which equals average molecule weight of repeat unit. For copolymers, this is calculated as the follows, using this equation. So molecule structure for polymers, and we have four commonly seen the molecular structures. First one is a linear. You can see this linear, and this chain we have secondary the bonding, which is usually kind of weak. Here is a branched. So here is one backbone. Here is another backbone. Each of these backbones, they have two branches here. A third one is cross-linked. And so you can see this is a backbone, another backbone, and these backbones, they are interlinked. And the fourth one is network. You can see, and they are networked. Okay, so this is the four very commonly seen molecular structures. And so this is the end for today's lecture. And in next class, I'm going to continue our talk about the polymer and structure. As I said, you need to pay attention to these basic concepts. And so the molecular weight, every number-based and weight-based, and polymerization, and how can we redefine polymer? How can we decompose polymer into two meaningful words, polymer, okay? And also there are polymerization, and also we have learned that the molecular structures for polymers, and also this polymer, they have a lot of very strange names, and you need to be very careful. And I hope you guys have a wonderful day for today. Thank you.